So how do we search for pulsars? Okay, the number one thing that you want to do if you want to find new pulsars is you need a really big radio telescope. Okay, pulsars are faint objects, and so we need a gigantic light bucket that will just let us collect as many photons as possible. So that's the number one thing. Okay, the second thing is you need a very clever electrical engineer, like this guy here, who's going to hook up some cables and digitize your signal so you can actually record this signal with very, very fast time resolution to a computer, and you can then search the data to look for pulsations. I'm not going to get too much into this diagram. Okay, I don't want to get too much into this either, but the basic idea I want to get across is that it's difficult to find these objects. We can't just point our radio telescope at a position in the sky and just look for something flashing and say, oh yeah, there we go, it's a new pulsar. Okay, they're quite faint. So what we have to do is we have to look at a position in the sky and typically point there for, say, 10 minutes or half an hour. We need to take data over a wide range of frequency and in little tiny individual channels so we can correct for this dispersive effect. And then we need to apply a bunch of fancy signal processing algorithms, things called Fourier transforms, to try to pull out this periodic signal from these time series. Okay? And so we do that, and occasionally we get lucky and we find a new signal. Most of the time, as some of the students who are working on pulsar searching, I think Jason's here somewhere, Jason will tell you that most of the time what you find is radio frequency interference from people's cell phones and their TVs and from satellites. So we need to sift through all that gunk. But every once in a while, we found a real new pulsar in the sky. So we look at plots like this. What we're looking for are pulse profiles that look like this. So this is the actual profile or the shape of one of these lighthouse beams of emission from a pulsar. And we have a whole bunch of other diagnostics. This is time. We like to see the pulsars on for long time spans. This is frequency. We like to see we detected over a bunch of frequencies. This is signal versus DM. So we look at plots like this to try to gauge whether a pulsar is real or not. OK, so just a tiny little historical overview of pulsar searching. Okay. So this shows the number of pulsars that we know of versus year. So here's when Jocelyn found the very first pulsar in 1967. By the way, this discovery was awarded a Nobel Prize to her advisor about 15 years later. And here's you can see the incremental discovery rate of pulsars through the years. I don't want to get into all these numbers here, but the main thing I want to point out is this dotted line. So this dotted line denotes about 1% of the total population. So we've still only touched the surface of the pulsars out there in the galaxy that we can find. The second thing I want to point out is this huge leap in the number of pulsars found from like 1998 until today. This is because of a really successful survey called the Parkes Multibeam Survey. This is a survey with the Parkes telescope in Australia, which has a multi-beam receiver, which means we can point at 13 positions on the sky at once and search for pulsars a whole lot faster. And I'll talk about some more pulsar surveys we're involved in a little bit. So it's really fun to find a pulsar. Once we find one of these new things, that's great. We can measure its period, or the rate at which it's spinning, right away. But that doesn't tell us all that much, right? We really want to learn a lot more things about the pulsar. We want to learn about its physics. We want to learn about whether it's in a binary system. We want to learn if there's anything really cool and interesting about it. So what we do when we find a new pulsar is we do something called time them, okay? And what this means is that we will look at the pulsar once a week and then once a month, once every few months, and we will time exactly how fast these pulses are coming at us, right? We can measure the period of these pulses very, very precisely. And we can effectively count every single neutron star rotation over time. Okay. So some of these pulsars are in binary systems with other stars. So they're actually moving like this. And so what we're going to see is that's going to affect their apparent pulse period, right? So if I'm coming towards you very quickly, as I'm coming towards you, my pulse period will appear to get faster. As I'm moving away, the pulses will appear to get farther apart. So this is called Doppler shifting. And so by looking at these Doppler shifts, we can actually figure out if a pulsar is in a binary system with another star. Of course, there's all these other things we need to subtract, right? We know that the Earth is moving around the sun. We know that our telescope might be at different positions on the Earth, and all that will affect how long it takes a signal from the pulsar to reach us. And so we need to have a really complicated model that takes into account all of these effects, right? But once we come up with such a model, then we can figure out really amazing things. We can figure out what kind of binary system the pulsar is in. We can figure out how big the orbit is. We can figure out how massive the companion is. All sorts of neat stuff. We need to worry a lot about observatories and having very good clocks at observatories and systematic effects. And this can be really tedious, but it's very important. And we get really nice physics once we can get rid of all these systematics and time things very precisely. Okay, so what are some of the things that we can learn about pulsars from timing them? Okay, so a really hot topic these days are extrasolar planets, right? So these are planets outside of our solar system orbiting other stars. Currently, we know of, 200 some of these extrasolar planets. Okay, the very first extrasolar planets ever found were actually found orbiting a pulsar. Not a normal star like our sun, but a pulsar. So how do we know that? Well, we can measure the periods of these pulsars to say 1 part in 10 to the 15, right? So really accurate measurements of the periods. This is actually a pulsar that I worked on when I was at Penn State as an undergraduate. I did not find the planets, but I worked with the professor who discovered the planets, which was really exciting. And you can see this is period versus time. And you can see that the period of this pulsar is doing all sorts of wonky things, right? So if the pulsar wasn't in a binary orbit, we'd expect the period just to be constant. But we see it going up and down and up and down and up and down and up and down. Okay? And this really puzzled pulsar astronomers. Okay? And what was figured out is that this pulsar is actually wobbling ever so slightly in this periodic fashion due to the motions of 3 planets around it. So the gravitational pulls of these little planets are just perturbing the motion of this pulsar ever so slightly and making the pulses appear to arrive a little bit sooner or a little bit later throughout the orbit of these planets. These planets actually have very similar to Earth masses. So it's actually quite a similar planetary system to our own, which is pretty odd because a pulsar is a very, very different star than a star like our sun. And it's still not clear how this thing actually evolved or how something like this formed. You would definitely not want to live on these planets. They would not be a very hospitable place to live. Okay, so let's talk a little bit more about what we can learn about pulsars by timing them. Okay, so one thing we learn is that even aside from a pulsar having planets or being in a binary orbit, we see changes in the pulse period. Okay, the reason for this is that just like people, pulsars slow down over time. Okay, so they're born spinning really fast, and then as they get older, they gradually lose energy and they slow down. Okay, so this plot shows period versus the rate of spin down of a pulsar. So when a pulsar is first born, it has a short period, and its rate of spin down is very high. So it's spinning down very quickly, and its spin period is shorter. And then it moves across the diagram like this, and eventually it hits this region called the pulsar graveyard. Okay? So in this graveyard, there are all these old dead pulsars, which are just spinning too slowly to actually accelerate particles enough so that we can detect the radio emission. Okay? We call this thing the period derivative or P dot sometimes. Okay? Now, you're probably really puzzled by this diagram, because I just said pulsars start up here, then they move slowly over into this way, and they die in the pulsar graveyard. And there's some scatter around here. Pulsars may be born with slightly different periods and spin down at slightly different rates. And you're probably wondering, well, what the heck are all these guys down here doing then? Right? So who are these very, very fast spinning pulsars that are spinning down very slowly? Okay, so these are a very special population of pulsars. We call these pulsars millisecond pulsars because they have periods ranging from, well, a millisecond up to something like 20 milliseconds. These pulsars are spinning very, very, very quickly. I don't know if you can see this very well, but you'll also notice most of them have little circles around them. These little circles around there are on there to denote that these are in binary systems. So most of these pulsars have binary companions.